quantification. Okay, so that's the classical examples. And the well-known, and they actually, even to undergrads, so they tell us how polymorphism fails, and there are many, many fixes. I'm not going to go through all of them. And as I said, one of the most easy and effective is the value restriction, which I've just described. But whenever I even teach that to the kids, I feel a bit of a fraud because I tell them how it fails, but I don't tell them why it fails because I don't know exactly why it fails, and I'll talk about this in a minute. I don't really understand why each fix works, and I would like to really understand how the fixes relate to each other. So I'm going to give a warning and apology. So I've jumped in on the bandwagon for submitting a work in progress talk. So I don't have all the answers. There's vast existing literature. So if you say, oh, this has been done by me, well, by you, 5 years ago, 10 years ago, 20 years ago, then yes, please, your name should be there, and let me know, please. Okay, so let's get going. Okay, so just go talk a bit about the how versus why. So I'm trying here for maybe a bit of higher standard of understanding. So we all know, we know why it fails. This is the error, but here it crashes. Okay, and if you look at Toft's paper on Hindley-Milner polymorphism, he gives a very nice explanation, operational explanation, of exactly this phenomenon. He says, well, we can't do it here because later on in the proof, things are going to go wrong. So the reason I'm being a bit picky here is I want to understand why this fails only in terms of this line. I don't want to look further. I want to understand why this fails. So I'm looking for some kind of local explanation. And for me, that means finding some kind of denotational semantics for these constructs because they aim to explain a phrase only in terms of itself. So if I get denotational semantics for Hindley-Milner polymorphism, then it should be obvious why I can't just add effects easily. Okay, and this is where I managed to recruit this category theorist called Sean Moss, who's a lean-mean category machine, and he helped me a lot here, so he could make it here, but lots of credit goes to him. And just as the outermost step, the first step, I'm going to separate Hindley-Milner type inference from the semantics, because I really think that what's happening here is a semantic issue, right? And the inference would come later once we work out the semantics. So I'm not going to talk about how you get those, how you work out which variables should be generalized. Just going to say things are generalized. And you're going to see that. Going to be seeing that in a bit. If you listen to Bob Harper, that's the explicit versus implicit typing rant. Okay, so what we're going to talk about. So first, I'm going to start with a pure calculus that only has nothing. It only has Hindley-Milner polymorphism in it, which makes it a bit boring, but it makes it clear what the structure I'm looking for. And I'm going to give you the syntax, the models, and some kind of easy sanity check theorem to make things work out, justifying a beta reduction. And then I'm going to briefly talk about how to add simple types to this calculus, because it really has nothing. It just has let polymorphism. And then I'm going to talk about adding effects, why it seems hard with the model, and different design choices that seem straightforward, and how existing solutions, so as I said, I want to understand how existing solutions solve this problem, the soundness problem, how they fall into place. So if you say, oh, you didn't mention this approach, then I'll be very happy to learn that because it might fit into one of these three things, which is good, or it might be a new one, which means I'll learn something new. So please do interrupt. Okay, so let's start with the calculus. Okay, so you see there's almost nothing in here. I've been very explicit about including stuff. So we have three kinds, either type or a scheme or context. Okay, and we have type variables and we have context of type variables. And then we have types, and types have nothing. It can just be one of the type variables in your context. Okay, and then you can use those types to create schemes. That means you generalize at the outermost level. And then with those schemes, you create contexts and terms. And the only terms you can have are, I have some polymorphic variable x and I specialize it with some tuple of types. Or I can generalize the type over term m according to some scheme, so according to some tuple of variables, and then continue then. So that's it. There's only let polymorphism here, nothing else. And that's kind of like the point, pinpointing what it is to be let polymorphism. Okay, and then the rules, once you have this in place, then the rules fall into place quite immediately. So we have to say when our types were formed, and when our schemes were formed, and when our contexts were formed. So there really is nothing to it. Okay, so how do I type a scheme? Well, if I have my context, my type variable context with some free variables alpha 1 to alpha n, and gamma never uses them, okay, but the type of M might use them, then I can generalize over them. Okay, so that's the type rule. And again, I remind you that things are explicit here. Okay, so the types are in the terms. Okay, so everything is explicit. I don't have type inference here. Okay. And terms are, again, what you'd expect. Okay, so if I have some variable x and I want to specialize it in a tuple of type tau, then look it up, find a scheme for it, make sure that lengths match up and do the substitution. And with the let is similar. Okay, so if I can type M with scheme sigma, extend the context with that sigma, and type N, then I can sequence them one for the other. Okay, and really this is just a fragment of Harper and Mitchell's core XML, which predates, for you youngsters, or us youngsters, the new XML. So this is explicit ML. It's not the data language. Okay. The difference, if you care about this, there's only specialized variables that have some kind of system, and it's very minimal. So they don't even have simple types, no products, no functions in this language. It's just really trying to pinpoint the Hindley polymorphism bit. Okay, so I'm not really taking credit for this language. Really, they did all the hard work way back then. Okay, so now let's look at the models. Okay, so the core idea is to take models for system F, which is a can of worms, because we don't even have set theoretic models, and just tweak them a bit and add some stuff. And this is the missing stuff. This is the stuff we have in the model for system F, and this is the new stuff that we've added. And here Sean was extremely useful. So thank you, Sean. And if you know about these models, so this is just the highlights, right, is we have a PL category, a lambda 2 fibration, and what we're doing is we relativize it according to some functor J. And relative is a precise term. If you know about relative monads, then it's that term. If you know about relative adjunctions, good for you. It's pretty good. You know your literature. That's from 68. And the reason I'm taking categorical structures is I really want to be able to compare lots of different structures, not just set theoretic concrete ones, because if I just wanted a concrete one, I could take the Harper-Mitchell model, which they gave back in '93. So they had a set theoretic model, because these guys do have set theoretic models. So what I'm going to do now is I'm very quickly going to go through the model structure, and I'm not going to give all those definitions because that's going to be a bit tedious, and I'm not sure what to get out of it, but I'm going to try to give the intuition, and I'm going to highlight how this concrete model comes into play there, and then we'll later see how to tweak it to get different variations and effects. Okay, so we go through this long tuple. So let's start. So this is a category with finite products. Okay, and this is where we're going to interpret our type variable contexts and type substitutions. Okay, so the objects are just the natural numbers in the concrete model. So if you think about concretely a set theoretic model, take the natural numbers, and a morphism from M to N is a tuple of functions where you put in some types for each of the type variables, and you get out another type. So U is a chosen set in which we interpret our types. Okay, and there's a kind of like a small versus large distinction here. You have types and you have schemes, and schemes are big and types are small. Okay, and we're going to be using that a lot. Okay, and the Cartesian structure in this concrete model is just M times N is M plus N, and the projection of M plus N is just forget all the extra stuff. Okay. Right, the next bit, okay, so this is a mouthful. We need the Grothendieck fibration with local finite products. So I'm not going to give all this definition. If you know it, good for you, pretty good. But the intuition is a bit like this. So what we have is we have a category D, and then over each context we have the stuff that lives over this context. They have all the schemes that have free variables in that context, and we have means to transfer between those categories. So each of them is a category where the objects are schemes and morphisms are terms within those schemes. Okay, and we have a way of translating from one to the other by doing the substitution. Okay, that's the kind of the intuition you should be should be having. And this is also the definition you should be having for system F. So there's nothing different here. Okay, and concretely what we're going to do is we're going to take each of those fibers, each of those categories. The objects would be functions, and this time we're going to assign schemes. They're going to be large. So once you give me which types to put in each of the M holes, we're going to give you back a set. Okay, and morphisms are once you give me those types, they're going to be a function going from, so if delta chooses those types, it's going to be just a function going from F delta to G delta. It's a morphism between F and G, and all these live over the same context. Okay, and reindexing is precomposition with substitution. Okay, so I'm going to write delta, S delta for things that live over delta. Okay. Now comes the different bit. So far it was just system F. Okay, so now comes the different bit. So we designate a subclass of S, which we call the types. Okay, all the small sets rather than the large sets. And we're going to take the inclusion from T to S. This is just an inclusion. This is a very set-theoretic definition. And we can take the fiber over every context. And concretely, that's going to be all those schemes that go into a type. Okay, so they look large, but they're actually small. Okay, and now once we have this piece of data, we can actually get a property out of it. We can construct another category called T delta J tau prime of sigma. So once we have a scheme and two types and in a context, we can create this category by just taking all the morphisms here. And that actually, once you collect all the structure, it collects into a nice structure called set to the S op delta enriched category. And the reason I'm highlighting this is because following Paul Levy's tricks for compact push value, this is what you need in order to get context from one category, but types in a different category. Okay? So this is what this gives me. And once I define this structure, I get a functor going from T to S, fiber-wise, and it behaves nice with the substitution, with the reindexing or the substitution, the type level substitution. Okay. So this is what you should take from this slide is give us the way to relativize small versus large. And this is where the extra spice comes in. Okay, so to finish the model definition, we need an object omega, which stands for all the types. Okay, and then we need to connect the types, which is this T guy, with our substitutions. Okay, and we do that by having a family of projections between the fiber over delta of types and all the substitutions into omega. We just pick those types once you give them the types to put in the holes. Okay, so if delta is a set of holes, okay, then you can choose the type that corresponds to filling those holes inside the substitution. Okay, so the type with the holes is like a substitution, okay, with one of one type. Okay, so concretely it's just going to be just one hole, and it's just going to be almost an identity. Okay, and the final bit, this is where everything sort of ties in. And again, if you've seen System F, it's almost the same, only something is a bit different. So if we take the projection we've seen earlier from delta cross delta prime to delta, and we reindex it, we get a functor, pi star 1, and then we're taking a right adjoint to that. But if you look carefully at the types, they don't work out. They live in different categories. So what you need to do is you need to take this functor j to relativize, to work out these categories together. This is what's called a relative adjunction, and you need some kind of back-Shepard condition to make sure that it's compatible with indexing. But what it amounts to is just saying, for every delta and delta prime, you have a new object, an object map for all delta prime that's sort of generalized over the variables in delta prime, and then a family of natural bijections between terms having this type with delta prime free variables that don't have delta prime variables in the context, and morphism into for all. Okay, so again, what I'm taking is that we'll just take the syntax and sort of break it down into categorical structure, so that now I could tweak it. Okay, so as I promised, there would be some sanity check. So if you go through all the trouble of defining what it means to substitute a polymorphic M in N, okay, for X, so that means whenever you have an X, there's some kind of type associated with it, then go to M, substitute that type for these alphas, and stick that in. So you can read that here. Okay, then the semantics for, in every model that I just described, the semantics of let x equals m in n is the same thing as doing substitution. So really things do agree. This is just a sanity check. It's not a deep theorem or anything, just making sure things work. Okay, and so this has to give us the core calculus. If you now want to look at something like core XML, like Harper and Mitchell's core XML, then you can add simple types. You can just add them, and then in the model you ask for each fiber to have products and exponentials and the reindexing to preserve them between the fibers. Things do work out and you extend the syntax. So this is, in a sense, it's not that interesting, apart from what's interesting in it is that we have actually managed to break down the structure into where the semantics are modular. You want to add extra stuff, this is the place where it goes. Okay, so now let's do the reason we're here is try to look at effects. Okay, so I'm going to make a uniform assumption, which is it's a bit stronger than what you need. Okay, but it will help me to relate the three different design choices that I identified. So what we're going to do is we're going to need something like a monad, because that's something like an effect, and we're going to have a monad of a fiber of schemes, and it needs to be stable under indexing. It needs to play well with reindexing. Okay, so and and this is again, as I said, a bit too strong. Once we fix on a design choice, we're not going to have all this structure in a syntactic model. So if you want to get a syntactic model, we might have to weaken this structure a bit just to get that. But right now I'm using the concrete models to try to compare solutions. Okay, so where's the problem now? Okay, so if we work in a core value setting, okay, so it's natural to interpret terms as morphism going from gamma into T of some type. Okay, but then how are we going to get interpretation for this? Okay, so I'm going to give three different obvious choices, and I'm going to relate them to solutions that seem to be out there, but I'm not saying it's exhaustive. I'm actually quite keen to find out that it's not exhaustive, because that teach me new stuff. Okay, but for now, this is the solve the trouble. It's not a very good answer for me yet, because it doesn't really explain reference cells, but it's for me it's the beginning of the trouble, because I'm only looking at let here. I'm not looking at anything else. So that's already a positive indication for me. Okay, so design choice number one. That easy. You look at it and you say, okay, so I have a map going into T of tau. Just take a bijection with that. So instead of taking a J relative adjoint, take a T relative adjoint. Okay, and you have to sort of, I'm skimming over some technical details, but that's roughly the story. And then what this amounts to is a call by name let. Okay, and that's because what you have here is all the effects taking place when you evaluate a value. So that means whenever you stick it back in, whenever you specialize an X, you cause those effects again. Okay, and that gives you a call by name behavior. You can do some kind of sanity check like theorem, and you can prove that. And it's not a new solution. I mean, so this is in Leroy has a paper from 1993 where he actually does this. So you have a monomorphic call by value, something like a denotation, and then you have a polymorphic call by name, let, and they play nice together in the language, and he implements a camel compiler, and he compiles it itself, and he checks that things work out, go and read that paper if you're interested in this solution. So as I said, I just want to understand the various solutions right now. So that's design choice number one, call by name. But it's a bit weird. It's not what gets implemented in OCaml, for example. Okay, so design choice number two. Okay, so we want to have a call by value let. So what we're going to need is if we have a morphism going into T, then we can quantify it with a for all. It turns out we always have this morphism, so we can always go from T for all into for all T, and that's not so surprising. You can think about it, and I can explain later how to do it. Okay, so if we have a morphism which factors through this other morphism, then we can give semantics to its polymorphic let. Okay, so this gives us kind of like a semantic condition as to when can I generalize over a term? Well, exactly when it factors through. Okay, so that's a bit iffy, but because it's very hard to check semantic properties in a compiler So one easy way where I can always guarantee this will happen is if I have a distributive law between for all and T and for all, but you have to make sure that the fibers work out. And if I have this, then all morphisms factor through. So then the question is does that ever happen? So if you just look at the concrete model we gave, it's very obviously not going to happen for very simple effects. So I've learned this from Alex Simpson. Well, I gave him the other spiel. He told me, oh yeah, but I've looked into it before in O3, and I think that if you look at the equational theory and you look at all the monads over that theory, then there is a model. So he was working with system F, so for him it was a realizability model, but now after we talked a bit, and we think there's also going to be a parametric model instead, which is going to be slightly nicer because you don't have to work over PCAs and other stuff like that, pairs. You can just work set theoretically, where you do get this distributive law. And so this is still a conjecture we're working on proving it, but once we saw, well, with Pretner, I was in Ljubljana just last week, we thought, well, let's try to get this into a language, right? If you have algebraic effects and handlers, so that's like a free equational theory, things are going to be easier. Can we just get rid of the value restriction and just have a core value less polymorphism? And it does work. Sam now tells me that's okay. So we're going to talk about this afterwards. So that appears to be new and cool for me, but maybe for you as well. So that's design choice number 2. How much time have I got on? 4 minutes. Okay. So the last bit, very quickly. Okay, we had all morphisms we can give core by name semantics. Some morphisms get a core by value semantics. The value restriction, if things are just values, it leaves way less morphism. It's the ones that factor through return. And for these ones, core by value and core by name behavior agrees. Okay? So it's not just we're asking for things to factor through. We say, oh, they're really core by name, but you can execute them as core by value. It's almost like a compile optimization. Okay? And then we'll say, okay, so this is a semantic property. When does that hold? And that goes to Carsten Fuhrman thesis, where he gives a criterion for when you can do that, when you can execute core by name as core by value, vice versa. It doesn't matter. It's called tankable. So you have this Venn diagram, and now I don't know whether the relaxed value restriction, what gets implemented in Garrigue's value restriction, whether it lives here or not. I mean, I don't know, but it's a conjecture I would like to find out. Okay, so just to summarize, so we've seen a calculus, syntax models, and some kind of sanity check, and we've seen different design choices we can make in order to address the soundness problem, and there's plenty of stuff to do left. So as I said, this is work in progress. I'm currently very interested in the parametric models for core by value because that's cool. But really to understand the problem, you need to understand reference cells and lists to look at the example from the beginning. I like that example because it's quite simple. You don't need higher order functions. You just need higher order state. You just need lists. Once I work that out, I want to look at adequacy, soundness, add effect handlers, inference, recursion, and yeah, this is a bit of an open one. We have this small versus large thing. Bob, did anything come out at the end with the algebraic set theory stuff and fibrations? Okay, so maybe there'll be something there. But, okay, that's it. So I'll take questions now, please.
So, just a general remark. I've been working on Cobra, a fact language, right? And so I run into the same problems, saying like, oh, let's say for now. And I always had this gut feeling, oh, it would be great to do a nice denotational semantics, a category theory. It was really difficult for me to follow. But maybe one day I'll get.
Well,
I think it's really cool work. Like I tried it and I always got stuck, and in the end, I kind of gave up. But I think it's really promising.
So I'm here for a week and a half, and I can come for longer if you want and explain it to you.
No, yeah, let's get together. But I think, yeah, cool stuff.
Thanks.